Beneath the rusty surface of Mars lies a secret that remained hidden for decades until a daring Chinese mission peeled back the layers of the red planet in a way no other rover had ever done before. In 2021, the Chinese rover Zhurong touched down on Mars and began probing beneath its dusty exterior, revealing strange geometric patterns buried nearly 35 meters underground. These unexpected findings are forcing scientists to rethink when and how water vanished from Mars, challenging long-held assumptions about the planet's history. Zhurong's journey began on May 14th, 2021, when it became only the second rover in history to land successfully on Mars. Weighing in at about 240 kilograms and powered entirely by solar panels, Zhurong was engineered to cover roughly 200 meters each Martian day. It carried 6 scientific instruments designed to unlock the mysteries of the planet. Its landing spot was no accident. Utopia Planitia, the largest impact basin on Mars and in the entire solar system, spanning an astounding 3,300 kilometers across. But Utopia Planitia is more than just vast, it's ancient. This region dates back to the late Hesperian period, somewhere between 3.7 and 3 billion years ago. The basin's floor is draped with materials from the Vastitas Borealis formation, a layer left behind by the sublimation of frozen water bodies. Over billions of years, this terrain has been shaped by weathering, wind-driven deposits and meteorite impacts. Scientists have long suspected that this northern lowland area once held a massive ocean. From orbit, they've pointed to possible shorelines, but those features have been controversial. The shorelines are anything but smooth, with elevation changes up to 10 kilometers in places, far from the level coastlines found on Earth. Zhurong's landing site was chosen specifically because it seemed like a prime spot to find ground ice at low to mid latitudes, sitting around 25 degrees north of Mars' equator. That's notable because polygonal terrain and signs of frozen ground processes are usually found above 30 degrees latitude. Zhurong touched down about 280 kilometers north of one proposed ancient shoreline and 500 meters lower in elevation, meaning if there had been an ocean, this spot would have been underwater or at least near the coast. The mission's goal was clear: seek out evidence of past water and ice. To do this, Zhurong was equipped with a ground-penetrating radar called ROPR, which operates on 2 frequency bands. The low-frequency channel, running from 15 to 95 MHz, can reach as deep as 80 meters below the surface, while the high-frequency channel, spanning 450 to 2,150 MHz, offers fine detail down to just 7 meters deep. This capability is significant. NASA's Perseverance rover, which landed months earlier, also carries ground-penetrating radar called RIMFAX, but can only probe about 10 meters deep. Zhurong's radar could dive nearly 8 times deeper. Originally planned for a mission lasting 90 Martian days, roughly 3 Earth months, Zhurong surpassed all expectations, operating for a full Earth year and journeying nearly 2,000 meters across Mars. In May 2022, it entered hibernation mode to survive the harsh Martian winter and was expected to wake up by December, but it never did. Dust accumulation on its solar panels during winter storms likely starved it of power, preventing it from reactivating. Though silent since May 2022, the treasure trove of data Zhurong gathered is still being analysed, revealing astonishing new insights. The first groundbreaking discovery came from the low-frequency radar data. Scientists at the Chinese Academy of Sciences Institute of Geology and Geophysics applied a method called time-frequency analysis, not just looking at vertical layers as usual, but examining horizontal lateral variations in the subsurface. This approach uncovered 16 anomalous low-frequency bands stretching beneath Zhurong's path. The radar data divided the underground into 3 distinct layers. The top layer, from the surface down to about 35 meters, showed uniform energy distribution, implying relatively consistent material like loose sediment mixed with rock fragments. Below that, from 35 to 65 meters down, the radar detected vertical bands with unusual low-frequency signals alternating with higher frequency sections. These bands appeared regularly along the rover's entire 1.2-kilometer traverse. Deeper than 65 meters, the radar signal became noisy and unreliable. Those vertical bands in the middle layer were the key to something extraordinary. Each of the 16 bands had a dominant frequency near 45 megahertz, noticeably lower than the surrounding background frequency of 52 megahertz. The research team carefully ruled out surface features like rocks or dunes as causes, since the terrain was relatively flat, with elevation changes under 10 centimeters over every 3-meter interval, and rover images showed no significant terrain variation. They considered and dismissed other possibilities such as noise artifacts or radar wave absorption by certain materials. The conclusion: these vertical bands represent infilled wedges between buried polygonal terrain, geometric patterns etched into Mars's subsurface billions of years ago and now hidden beneath 35 meters of overlying material. While polygonal terrain is common on Mars's surface, especially at higher latitudes, this was the first time such structures were detected underground. The polygons averaged about 67 meters across, with wedge widths around 27 meters and vertical heights near 30 meters. Understanding these dimensions helps identify how these polygons formed. Polygonal ground can arise from several processes: mud cracks from drying, columnar jointing in cooling lava, tectonic fractures, or thermal contraction cracking caused by freeze-thaw cycles. The team analysed each possibility. Mud cracks typically produce ratios of wedge width to polygon diameter below 0.1, whereas these buried polygons had a ratio of 0.4, ruling out drying mud cracks. Volcanic columnar jointing would create strong radar reflections at lava boundaries, but none were observed, and the nearest volcanic vents are over 1,700 kilometers away. Tectonic faulting tends to produce long linear features, contrasting with the intermittent networked bands detected. That left thermal contraction cracking, the process where freezing ground shrinks and cracks, later filled with water, ice, or sediment. On Earth, thermal contraction creates 3 types of polygonal ground: ice wedge polygons filled with ice, composite wedge polygons with ice that has sublimated and sediment partially filling the cracks, and sand wedge polygons filled by wind-blown sand. The buried polygons detected by Zhurong most likely formed this way, pointing to a cold climate involving freeze-thaw cycles and the presence of water or ice. Here's the twist: these polygons lie at a latitude of 25 degrees north, a low to mid-latitude on Mars. Today, polygonal terrain on Mars mostly appears above 30 degrees latitude, where conditions are colder. For these polygons to have formed back then, the climate must have been much colder at this location. One explanation involves Mars's axial tilt, or obliquity. Currently, Mars tilts about 25 degrees, similar to Earth's 23.5 degrees. But Mars' obliquity swings dramatically over hundreds of thousands to millions of years, ranging between about 15 and 35 degrees. During periods of high obliquity, the poles receive more sunlight, causing polar ice to sublimate and redistribute toward the equator, possibly chilling mid-latitudes enough to form polygonal ground through freeze-thaw cycles. The sharp contrast in radar signals above and below 35 meters suggests a significant change in Mars' environmental conditions. Above that depth lies relatively uniform sediment, while below, complex polygonal structures reveal a history of colder, wetter conditions. Researchers interpret this as evidence of an ancient wet environment that ceased, leaving the polygonal terrain to be buried under 35 meters of new deposits over billions of years. Meanwhile, the high-frequency radar shed light on the shallow subsurface down to about 7 meters, offering unprecedented detail using a sophisticated quad polarization system. This system operates in 4 modes: HH, where both transmitting and receiving antennas are horizontally polarized; VV, both vertically polarized; HV, transmitting horizontal and receiving vertical; and VH, transmitting vertical and receiving horizontal. These different polarizations help distinguish between horizontal layers and tilted or fractured features. The high-frequency data revealed 3 layers in the top 7 meters. The uppermost layer, from the surface to about 0.65 meters deep, showed weak radar reflections consistent with loose, unconsolidated sediment, weathered material mixed with windblown sand and small rocks. When Zhurong landed, its retro rockets blasted a hole nearly 0.4 meters deep, and cameras captured images of this excavation. The hole exposed layered gravel and sandy sediments that matched the radar's depiction of this top layer perfectly. Together, these findings from Zhurong's radar paint a rich picture of Mars' geological past, one marked by shifting climates, buried ice-related features, and a subsurface landscape more complex than ever imagined. Beneath the surface of Mars, a story unfolds, one that rewrites what we thought we knew about the planet's watery past. Scientists have uncovered a complex underground landscape marked by layers of sediment, ancient shorelines, hidden craters, and subtle signs of water's long-gone presence. Starting from just under 2 feet deep, the middle layer stretches down nearly 13 feet below the surface. This section stands out with its strong radar reflections, hinting at more solid, possibly cemented sedimentary rock. Below it lies a deeper layer, extending from about 13 feet down even further, but with weaker radar signals that suggest a different, perhaps softer or more plastic material makeup. The real intrigue comes from the details hidden within these layers. Scanning across nearly 2 kilometers, the rover's radar revealed consistent parallel slopes dipping gently northward between 8 and 15 degrees. These aren't random inclines, they resemble coastal sediment slopes formed by waves and tides on Earth. On our planet, beaches and shorelines display similar angles, shaped by water's energy moving sediment along the shore. The degree of slope correlates with wave strength. Steeper slopes mean stronger waves. The slopes detected here average about 14.5 degrees, falling right in the middle of the range seen in 21 different Earth coastal sites. These slopes correspond closely to what geologists call foreshore deposits, the zone between low and high tide marks where sediments accumulate over millions of years. Waves carry and spread materials from rivers, building these sloping deposits as they advance or retreat with the tides. Alongside the slopes, radar also uncovered fractures within the middle layer. Some were tiny and isolated, while others cut deeply, extending into the bottom layer. One fascinating feature, labeled F8 in the research, presents as a concave-up fault dipping south. At its top, the fault is steep but flattens out deeper down, a pattern typical of plastic deformation seen in sediments rich in salts or clays. Unlike hard rock that snaps under pressure, these materials bend and warp, suggesting the bottom layer contains soft, pliable deposits, likely saturated with salts or clays. Even more compelling were 2 buried impact craters found beneath the surface. The first lies about 4 feet deep along the rover's path and measures roughly 36 feet across, buried under less than 2.5 feet of sediment. The second crater sits deeper, nearly 13 feet beneath the surface, with a similar diameter but thicker sediment fill. The rover even imaged this deeper crater twice by making a U-turn, confirming its presence with perfectly symmetrical radar images. These craters tell a story of sequential sedimentation. The deeper one formed first, was gradually buried by 4 meters of sediment. Then the shallower crater appeared and was finally covered by less than a meter of material. What could cause such widespread, layered sedimentation? The answer points squarely to flooding, water-driven sediment deposits that spread evenly across the landscape, burying craters and shaping the terrain. The evidence all supports a shallow, aquatic environment, likely the shoreline of an ancient Martian ocean or a large, long-lasting sea. Multiple lines of evidence back this up. First, the steady northward tilt of sediment layers matches angles seen in Earth's beaches. Second, these sloping deposits stretch continuously over more than a kilometer perpendicular to the proposed shoreline, indicating a large-scale environment. Third, Electrical measurements of the subsurface materials align with fine to medium-grained sand and silt, typical of coastal sediments. Fourth, surface observations reveal sedimentary rocks with bedding laminations and layered structures characteristic of water-laid deposits. Some rocks contain sulfate minerals like gypsum, basanite, and epsomite, minerals that form only in the presence of water. Lastly, the radar detected centimetre-thick laminations within the middle layer, patterns that resemble tidal or wave-driven sedimentation cycles, where each thin layer represents a single depositional event, such as a tide or storm. Scientists considered other possibilities too. Could rivers have created these layers? Fluvial deposits can produce slopes, but they typically show channels and erosion features, none of which were observed here. Could wind-blown sand dunes explain it? Aeolian deposits often have variable slope angles and cross-bedding patterns, but the radar data showed consistent parallel slopes without cross-lamination. What about volcanic lava flows? Lava has much higher electrical permittivity and tends to create strong reflections between layers, but these were absent in the radar data. Each alternative failed to match the observations, leaving coastal deposition as the most likely explanation. If Mars had an ocean here, it wasn't a fleeting puddle. The continuous foreshore deposits over more than a kilometre indicate a shoreline that prograded outward over millions of years. This process requires sustained wave energy, a steady sediment supply from rivers, and crucially, time, often tens of millions of years. On Earth, beaches of similar thickness take at least 10 to 40 million years to accumulate, with sedimentation rates of around 10 to 40 centimetres per thousand years. The grain size of the sediments, fine to medium sand, suggests transport over long distances, likely from rivers flowing in from southern highlands. If the sediments came from local cliffs, they'd be coarser, yet no nearby river channels were detected, implying sediment was carried in from afar. Putting it all together, around 3.5 to 3 billion years ago, during Mars's late Hesperian to early Amazonian period, this site rested along the edge of a vast ocean or sea. Rivers delivered sediment that waves and tides spread along the shore, gradually building the beach outward over millions of years. This explains the layered, sloping deposits seen in the radar data, each layer marking a different stage in the shoreline's evolution. Eventually, the water vanished. Mars's climate shifted, cooling and drying until the ocean either froze, evaporated, or sublimated into space. Without water, sedimentation stopped and the beach was exposed to the harsh Martian atmosphere, beginning a slow process of weathering. But the story doesn't end there. Buried polygons, patterns formed 3 to 4 billion years ago, coincide with these ancient beach deposits, leading scientists to believe Mars entered a global dry phase roughly 3 billion years ago. For decades, the prevailing view was that Mars has been dry ever since, aside from brief localized melting triggered by volcanic or impact events. These new radar findings challenge that timeline. The layers closest to the surface tell a different tale, one of ongoing water activity much more recently than previously thought. The bottom layer, extending from about 13 feet deep and reaching even further below, matches the Vastitas borealis formation sediments from the late Hesperian era. But the middle layer, spanning roughly 2 to 13 feet deep, shows clear signs of sedimentary activity involving water. It features consistent northward slopes, well-preserved buried craters, and centimetre-scale laminations interpreted as platy structures or duricrusts, hard mineral crusts that form when water evaporates, leaving minerals behind. On Earth, duricrusts appear in arid or semi-arid regions where periodic water evaporation occurs, suggesting that water persisted at the Zhurong site long after the deep sediments were laid down. To pin down the timeline, researchers counted impact craters on the surface and compared their sizes and frequencies to known Martian impact rates. They found that the surface materials and the top few meters are surprisingly young, only about 757 million years old. In Martian geological terms, that places them in the middle to late Amazonian period, an era traditionally considered dry. Yet the characteristics of the middle layer, its uniform thickness, continuous slopes, buried craters, and fine laminations, paint a picture of sediment accumulating in a shallow aquatic environment well into this supposedly dry period. This discovery forces a rethink of Mars's hydrological history, suggesting that water lingered on the surface much longer than previously believed. This discovery challenges everything we thought we knew about water on Mars, showing that liquid water stuck around on the surface much more recently than anyone expected. But don't get the idea that Mars was covered by a massive global ocean during this time. The evidence points to something more modest, a shallow lake or maybe groundwater pushing up to the surface when Mars' tilt or obliquity shifted dramatically. Here's the picture researchers are painting. When Mars's axis tilts more steeply, ice from the polar cap sublimates, turning directly from solid to gas, and then redistributes closer to the equator. This ice can pile up underground at lower latitudes. Later on, as temperatures fluctuate, that buried ice might melt, causing temporary flooding on the surface. Another way water could reach the surface is through a process called cryogenic suction. In this situation, freezing temperatures near the surface create a pull, drawing moisture up from underground aquifers. As ice forms close to the surface, it generates a pressure difference that sucks more water upward. This leads to the formation of ice lenses beneath the surface, and during warmer spells, that ice could melt into liquid water visible from above. Either way, the key takeaway is that the area where the Zhurong rover landed experienced ongoing watery activity as recently as 750 million years ago. Water wasn't just a fleeting visitor. It lingered long enough to lay down a consistent sediment layer roughly 4 meters thick, spreading evenly over a wide area. That's a game changer for several reasons. First, it pushes back the timeline of when Mars could have supported life by hundreds of millions of years. If liquid water existed until that time, it means potential habitats for life lasted far longer than previously thought. Second, it tells a more complicated story about Mars's climate. Instead of a single sharp shift from wet to dry 3 billion years ago, the drying out was a gradual, patchy process. Some regions dried up early, while others like Utopia Planitia held onto water activity much longer. Third, this changes where scientists might look for signs of past life. Shallow lakes and subsurface water pockets could have been refuges for microbial life even after the planet's surface became harsh. And finally, it affects our understanding of present-day Mars water reserves. Much of that ancient water probably still exists underground, locked as ice or trapped within minerals. In fact, seismic data from NASA's InSight lander recently suggested there might be enough liquid water stored in fractured rocks beneath Mars's surface to cover the entire planet in a layer 1 to 2 kilometers deep. If even a small fraction of that water can be accessed, it could be a vital resource for future human missions. Putting all this in context, the findings from the Zhurong rover add a fresh chapter to decades of Mars exploration. Way back in the 1970s, the Mariner 9 orbiter first spotted networks of valleys and other signs that water once flowed across the planet. The Viking landers gave the first up-close images of the Martian surface and found polygonal patterns in the northern hemisphere. Later, the Mars Global Surveyor mapped possible ancient shorelines and provided detailed topography. The Mars Odyssey orbiter detected hydrogen signals hinting at subsurface ice, while Mars Express used radar to uncover massive underground ice deposits in multiple locations. On the ground, rovers like Spirit and Opportunity found minerals that form only in the presence of water, hydrated sulfates and clays. Opportunity famously spent years studying sedimentary rocks in Meridiani Planum, which formed in watery environments. Curiosity dug into mudstone layers in Gale Crater, discovering organic molecules and signs of repeated wet and dry cycles, all pointing to a past where conditions could have supported life. Right now, Perseverance is investigating a river delta inside Jezero Crater, collecting samples that will one day be brought back to Earth. It's also using ground-penetrating radar to scan for buried layers, though it's still unclear whether those are sedimentary or volcanic. Now, Zhurong has provided direct evidence of ancient beaches, buried polygonal terrain, and surprisingly recent water activity at low latitudes. These discoveries are filling in gaps, but also raising new questions. For instance, when exactly did Mars host a stable ocean, and how long did it last? The northern lowlands seem to have been underwater during the late Noachian to early Hesperian period, roughly 4 to 3.5 billion years ago, but scientists still debate the details. Some argue the ocean came and went multiple times, influenced by shifts in Mars' tilt and volcanic releases of greenhouse gases. Others think the ocean was more stable, lingering for hundreds of millions of years before drying up as Mars lost its atmosphere. Which brings up another mystery. Where did all that water go? The polar ice caps hold some, but nowhere near the amount suggested by the ancient shorelines and sediment deposits. Some water escaped into space over time, stripped away by solar winds after Mars lost its protective magnetic field. But recent studies, including those InSight seismic readings, hint that vast quantities still lie hidden underground. The biggest question remains, did life ever take hold on Mars? The environments uncovered by Zhurong and other missions, shorelines, shallow lakes, cycles of wet and dry, are exactly the types of places where life arose on Earth. If life did emerge on Mars during the late Noachian or early Hesperian, it had hundreds of millions of years to evolve before the surface became inhospitable. And if life developed, could it have survived underground as the surface dried? Microbes on Earth prove astonishingly hardy, thriving in deep subsurface caves, frozen permafrost, and the driest deserts. It's entirely possible that Martian life, if it existed, found refuge underground. The discovery that water activity persisted as recently as 750 million years ago opens the door to the idea that these habitats stayed viable far longer than expected, not billions, but hundreds of millions of years ago. Geologically speaking, that's practically yesterday. There's a bittersweet twist to this story though. The Zhurong rover, which made these groundbreaking discoveries, has gone silent. It entered hibernation back in May of 2022 to survive the harsh Martian winter. The hope was it would wake up on its own when sunlight returned in late December, but that never happened. NASA's Mars Reconnaissance Orbiter has taken images confirming Zhurong hasn't budged since then. It's still sitting on the Martian surface, but it's not responding. Engineers suspect dust is the culprit. Mars is notorious for its dust storms, some lasting months and blanketing entire regions. Even without global storms, local dust devils and wind keep depositing fine dust on everything. Zhurong's solar panels probably became coated with dust during the winter, blocking sunlight and preventing the rover from generating enough power to reboot. This fate mirrors what happened to NASA's Opportunity rover, which lasted nearly 15 years before a massive dust storm in 2018 cut off its power, and it never came back online. Exploring Mars is tough. The planet's environment is brutal. Dust, extreme cold, radiation, and a thin atmosphere all conspire to wear down equipment and end missions. But even when the machines go silent, the treasure trove of data they collect lives on. During its roughly 1 year of operations, Zhurong covered just under 2 kilometers, about 1,921 meters. In that short journey, it gathered data that has completely reshaped understanding of Mars's watery past. The buried polygonal patterns, ancient beach deposits, and signs of water activity. None of this would be known without Zhurong's work, and scientists are still digging through the radar images, spectroscopic data, and photos. The first wave of research papers is just the beginning. More discoveries are sure to come. Looking ahead, China is planning a Mars sample return mission, possibly launching in 2028 or 2030. Although the exact landing site hasn't been announced, Utopia Planitia, near where Zhurong landed, is a prime candidate. Bringing samples back to Earth would allow scientists to conduct detailed analyses impossible with rover instruments, precise age dating, mineral studies, searches for organic compounds, and even signs of life. Meanwhile, other missions continue Mars exploration. Perseverance is actively collecting samples in Jezero crater. Europe's ExoMars rover, named Rosalind Franklin, is scheduled for launch later this decade and will carry a 2-meter drill and ground-penetrating radar to dig beneath the surface. NASA's Mars Reconnaissance Orbiter and ESA's Mars Express keep watching from orbit. New missions from the United States, Europe, China, India, and the United Arab Emirates are in the works. Each mission adds another piece to the puzzle, revealing a Mars that was once far more dynamic and hospitable than the barren desert planet seen today. Yet, a paradox remains at the heart of Mars's story. The evidence for ancient water is overwhelming. Valleys carved by rivers, lake beds, deltas, shorelines, sedimentary rocks formed in water, hydrated minerals. But Mars is a small world, only about 11% the mass of Earth. That means its gravity is weaker, making it harder to hold onto an atmosphere. Without a thick atmosphere, Mars can't trap heat. Today, average surface temperatures hover around -60 degrees Celsius, far below water's freezing point. And without enough atmospheric pressure, liquid water can't survive on the surface. It either freezes solid or sublimates directly into vapor. So how did Mars ever maintain stable liquid water at the surface? This is the climate paradox, one of the biggest puzzles in planetary science. The leading idea is that early Mars had a thick atmosphere rich in carbon dioxide and other greenhouse gases. These gases would trap solar heat, warming the planet enough for liquid water to exist. But climate models struggle to recreate this warm, early Mars scenario. The catch is that the Sun was about 25 to 30% less bright 4 billion years ago, a problem known as the faint young sun paradox. To counter that, Mars would have needed atmospheric pressures much higher than the geological record suggests, or additional greenhouse gases like methane or hydrogen. But where would these come from? Volcanism is a strong candidate. Mars was volcanically active in its youth, releasing carbon dioxide, sulfur dioxide, water vapor, and other gases. Intense volcanic activity could have periodically thickened the atmosphere, warming the planet enough for oceans or lakes to form temporarily. Another possibility is that meteorite impacts, which were frequent during Mars's early history, could have produced short-lived warming events, releasing gases and melting ice. The story of water on Mars is complex, layered, and still unfolding. Every discovery, from orbiters to rovers like Zhurong, adds depth to the mystery of how this once potentially habitable world transformed into the cold desert we see today. Massive impacts on Mars unleashed unimaginable energy, instantly vaporizing rock and ice and creating thick, temporary atmospheres that could have trapped heat for thousands, maybe even millions of years after each collision. Early Mars was pummeled relentlessly by meteorites, which might explain those brief warm spells scattered throughout its history. Another intriguing idea is that Mars's axial tilt, its obliquity, changed far more dramatically in the past than it does now. When the tilt swings high, polar ice sublimates and redistributes toward the equator, boosting atmospheric pressure and possibly triggering greenhouse warming by altering how ice and dust are spread across the surface. Yet none of these theories fully crack the case. The mystery remains. How did Mars maintain stable liquid water on its surface for what could have been hundreds of millions of years? This puzzle just got more complicated thanks to discoveries from China's Zhurong rover. Evidence now shows water activity persisted not only during Mars's ancient Noachian and Hesperian periods, but well into the Middle Amazonian era, much more recent than scientists expected. One explanation could be that this water wasn't the classic surface rivers or lakes. Instead, it might have been groundwater seeping upward during epochs of high axial tilt or snowfall that briefly melted during warmer times. Alternatively, the region around the Zhurong landing site may have had unique local conditions, maybe geothermal heat from underground magma or a landscape that created a microclimate trapping moisture. These are all possibilities, but for now, they're just educated guesses. This is the nature of science: collecting data, forming hypotheses, testing them, and revising what we think we know when the evidence doesn't fit. Mars's climate history is clearly more intricate than a simple story of wet early days turning into a dry, barren desert. Instead, it was a patchwork of multiple phases, regional differences, and episodic events. The narrative is messy, but endlessly captivating. Now, the big question driving much of this fascination is life. Not just water or climate, but whether Mars ever supported life, and if so, whether any trace of that life still lingers. Life, as we understand it, needs three essentials: liquid water, organic molecules, and a source of energy. Mars had all three during the Noachian and Hesperian periods. Liquid water flowed or pooled on the surface. Organic molecules arrived on meteorites and were also created through volcanic activity and atmospheric chemistry. Energy came from sunlight, geothermal sources, and chemical reactions underground. The environments Zhurong explored are particularly tantalizing for astrobiologists. Ancient shorelines, shallow bodies of water, and cycles of wetting and drying. These are exactly the kinds of settings where life is believed to have first sprouted on Earth. On our planet, the earliest signs of life date back to around 3.5 to 3.8 billion years ago, preserved in fossilized microbial mats called stromatolites and carbon isotope patterns consistent with biological processes. These fossils come from ancient rocks formed in shallow marine environments, much like the shorelines and shallow lakes Mars had at the same time. Cycles of wetting and drying are especially important because they concentrate organic molecules, promoting the chemical reactions that build complex compounds like RNA and proteins. Tidal zones mix nutrients, and sunlight provides the energy needed to kickstart life. Given that life emerged on Earth under such conditions, it's entirely plausible that Mars, during similar periods, could have followed the same path. But here's the catch: if life did arise on Mars, can we actually detect it today? That depends on what kinds of biosignatures we're searching for. Fossils are one option. On Earth, microbial fossils have survived billions of years, but they're tiny and rare. Over billions of years of geological upheaval, burial, heating, fracturing, erosion, most would likely have been destroyed. Detecting them would require drilling deep into ancient rocks and examining them under powerful microscopes, something current rovers simply can't do. Another clue would be organic molecules. Life tends to produce organics with specific structures and isotope ratios that are hard to replicate through purely chemical, non-biological processes. Perseverance rover has already detected organic molecules in Jezero crater. The challenge is that organic compounds can also form without life, making it tricky to draw firm conclusions. Mineral deposits provide a third avenue. On Earth, certain minerals like iron oxides, sulfates, and carbonates form through biological processes. If similar minerals with telltale textures or compositions were discovered on Mars, that would be strong evidence. Lastly, patterns such as seasonal changes in atmospheric methane, variations in mineral deposits linked to water availability, or structural features like layered mats or branching filaments could hint at biology. Yet these patterns alone rarely offer definitive proof. The biggest hurdle is Mars's geological past. The planet has been active for billions of years. Rocks get buried, heated, fractured, and eroded. Radiation and oxidation break down organic compounds. Biosignatures fade away. The older the rocks, the harder it is to find anything preserved. This makes Zhurong's findings about water activity as recent as 750 million years ago especially exciting. If water was present at the landing site that recently, any life there would be far younger than the ancient Noachian life scientists have mainly focused on. Younger rocks are less altered, meaning biosignatures would be better preserved and easier to detect. Of course, that assumes life was still around 750 million years ago. If life emerged during the Noachian and then vanished as Mars dried out, even these younger layers might hold no biological traces. But if microbes found a way to survive underground in aquifers or ice layers, this recent surface water activity could have brought signs of them closer to the surface, within reach of current drilling technology. That's why sample return missions are so critical. Detecting biosignatures with certainty demands sophisticated tools, mass spectrometers, electron microscopes, isotope ratio analyzers that are only available in Earth-based laboratories. Perseverance is already collecting samples that will eventually be sent back to Earth by future missions. If samples from the Zhurong landing site can also be returned, they'd offer a second, independent data set from a completely different Martian region. This would be invaluable in painting a fuller picture. So what's the bottom line? China's Zhurong rover had a brief mission on Mars, just about 1 year, traveling less than 2 kilometers before going silent, likely forever. But in that short window, it transformed our understanding of the red planet. It discovered polygonal terrain buried some 35 meters underground, evidence of freeze-thaw cycles during the late Hesperian period. It captured images of ancient beach deposits with slopes and layering typical of coastal environments. And it revealed signs of liquid water activity as recent as 750 million years ago. Each of these findings challenges long-standing assumptions. The polygonal terrain at low latitudes points to a much higher axial tilt in Mars's past. The ancient shorelines beneath the surface lend strong support to the idea that oceans once covered parts of Mars. And the recent water activity pushes back the timeline of habitability by hundreds of millions of years. But every answer leads to new questions. How long did that ancient ocean last? Where did all that water go? Why do climate models struggle to recreate a warm early Mars? And above all, did life ever take hold there? The truth is, we don't have all the answers yet. But with every mission, every rover, every sample, we edge closer. Zhurong uncovered ancient beaches. Perseverance is exploring an ancient river delta. Future missions will drill deeper, analyze samples, and continue the hunt for signs of life. Mars tells a story of transformation, a planet that shifted from warm and wet to cold and dry, possibly once home to life but now inhospitable. Yet beneath the surface, hidden under layers of dust and sediment, the evidence remains, waiting to be uncovered. Zhurong found a glimpse of that buried history. Though silent now, its legacy echoes through the data it sent back, the questions it raised, and the new paths it opened for exploration. Mars was once a world of oceans and rivers, beaches and shorelines, freeze-thaw cycles and shallow lakes, and perhaps, just maybe, life itself. What China's rover revealed beneath the Martian surface isn't just geology, it's a window into a lost world, a planet that in many ways wasn't so different from Earth. Understanding Mars helps us grasp how planets evolve, how climates shift, and how life emerges, adapts, and sometimes disappears. For now, the search continues. The answers lie buried beneath the dust, waiting for the next explorers to bring them to light.